So over the last two videos, we've seen how to describe the state of a qubit. In this video, we'll see how to change the state of a qubit. In particular, we'll introduce our very first example of what's called a quantum logic gate. So what a quantum logic gate is, or what it does, is it's a way of manipulating quantum information, or manipulating the quantum state of a qubit or of a set of qubits. They're the basic building blocks of quantum computation, as well as doing other information processing tasks, such as quantum teleportation. So the example I'm going to give in this video is a very simple single qubit gate, the so-called quantum NOT gate. And as you can no doubt guess, the quantum NOT gate is a generalization of the classical NOT gate. And what it does, at least on the computational basis states, is exactly the same as the classical NOT gate. So it takes the 0 computational basis state to the 1 computational basis state, and vice versa. So it really is a very simple logic gate, a simple way of manipulating information. The reason I'm explaining it here is in part, well, it's important in its own right, but it's also that many of the ideas behind the NOT gate extend to many other more complex quantum logic gates and more complex quantum computations. Okay, so that's the action of the quantum NOT gate on the 0 and 1 states. But of course, those aren't the only states possible in a quantum computer or in a quantum bit qubit. You can also have superposition states like this. What does the quantum NOT gate do to that? Well, there are many possible actions which are consistent with these two actions. You can have all kinds of complicated dynamics, but in fact the quantum NOT gate does sort of the simplest possible thing. It acts linearly, meaning that it gets taken to the corresponding superposition of 1 and 0. So the 0 over here gets flipped to 1, and the 1 over here gets flipped to 0, and the superposition otherwise gets preserved. So that's sort of a very algebraic way of writing down the action of the quantum NOT gate. When it's in an actual quantum circuit, or there's an alternate representation, the quantum circuit representation, which for a NOT gate I'll depict here. So what is this quantum circuit? Well, this line is what's called a quantum wire. And basically it represents a single qubit. So we sort of imagine over here, this is the qubit initially in this state, whatever it is, goes along, nothing happens through the quantum wire. Well, then a quantum logic gate is applied. The quantum NOT gate is actually denoted by an X for historical reasons that we don't need to get into right now. So that manipulation is done on the state of the qubit, and then the quantum wire just continues and leaves the desired output. Okay, so that's the matrix representation. Sorry, that's the quantum circuit representation of the quantum NOT gate. There's another representation, a matrix representation of the action of the quantum NOT gate. So let me describe that representation. It's the action of the NOT gate can actually be represented in terms of this matrix, 2 by 2 matrix. And to see why that's the case, well, we want the NOT gate, the X, on 0 to produce the 1 state. Well, what happens if we look at the this matrix acting on the vector corresponding to the 0 state, which is just the 1, 0, as we've seen? It produces 0, 1, just the first column actually, because it's that we've got a 1 up here. And that is indeed the 1 state. And furthermore, if you use this matrix again, in here acting on the 1 state, well, you can go through, same basic deal, 0, 1, 1, 0, acting on, it's the 0, 1 vector. That gives you 1, 0, the second column here, which is the 0 state. And matrices act linearly on vectors, so indeed we know, since it gives the right action on the 0 and the 1 state, that it must give this matrix must give the right action on an arbitrary quantum state. So this is a correct matrix representation. Okay, so that's a very simple example of a quantum logic gate, and indeed it's a simple example of a quantum circuit, this guy, and a quantum computation. There's actually an even simpler quantum circuit, the simplest quantum circuit of all, and that's this, just a single quantum wire. This is sort of the simplest possible quantum circuit, or the simplest possible quantum computation. And it's tempting to regard this. So what does this do? It of course, it's just a single qubit being preserved in time. So whatever the input is over here, let's call it the state psi, which might be alpha 0 plus beta 1, is also the same as the output over here on the right. And it's tempting to regard this as completely trivial, but in fact, a quantum wire is, in many systems, the hardest thing of all to implement. Quantum states tend to be very fragile, partially because they're usually implemented in very, very small systems, single atoms, single photons. And because of that extreme sort of smallness, they are very fragile, and they tend to sort of get perturbed very easily by their environment. So this quantum wire is, in many cases, actually the hardest element of all to do in a computation. Okay, so that's quantum wires. Let's get just a little bit of practice in thinking about the quantum NOT gate. Let's ask ourselves a question. Let's analyze a simple quantum circuit. This is one with 2 NOT gates in a row. And you can probably guess what it does, but let's just work through the mathematics. So if the input state here at the left is alpha 0 plus beta 1, it gets changed by the first NOT gate to alpha 1 plus beta 0, and that gets changed by the second NOT gate into alpha 0 plus beta 1. So we flip the 0 to the 1 and the 1 to the 0, and then we do the same thing again, the second NOT gate. And of course, what that means is that nothing has happened, that the input qubit over here is the same as the output qubit. So in fact, this is equivalent to just doing a quantum wire. This quantum circuit is effectively equivalent to a simple quantum wire. There's another way of seeing this, or proving it. Imagine that the input over here, let's call it psi. Well, what happens to psi? It gets taken, first of all, to x psi by the first gate, and then this gets taken to x times x psi, which is by the second gate. And so if we want to understand the effect of the circuit, then we can just compute what happens when we use the matrix X twice, when we multiply it by itself. So 0, 1, 1, 0 times 0, 1, 1, 0. And that's equal to, let's go through, let's look at the top left-hand corner. So it's 0 times 0 plus 1 times 1 is 1. The top right-hand corner, we get 0 times 1 plus 1 times 0 is 0. Bottom left corner, 1 times 0 plus 0 times 1 is 0. Bottom right corner is 1 times 1 plus 0 times 0 is 1. So that's the identity matrix, the 2 by 2 identity matrix. And as a result, whatever the input is gets taken to the identity times the input, which is just the same as the original input. So this is sort of a more algebraic way of seeing that the effect of 2 NOT gates in a row is just the identity. Okay, so that's a simple introduction to the quantum NOT gate. Of course, the quantum NOT is, as we've seen, a very simple, almost classical gate. In the next video, we're going to see our first example of a really truly quantum gate, something that does involve superpositions in a very non-trivial way in the output, and that's the so-called Hadamard gate.